to address these questions from a different angle. One is from what have we learned in the history of 80 years of computing, and the other one is who will consume the working compilers that is done. I want to go back to the point of remembering that we want to satisfy programmer needs. Some of that is we need to satisfy the fact that those needs are for iterative development. Programming is an inherently good medium for sloppily formulated ideas, as Minsky said. Especially when we are in this age where we are looking for quantum applications, we need to enable very quick turnaround times. The other point is that good compilers tend to support idioms, and idioms are constructs that appear repeatedly across programs. That implies that we have representations that allow those idioms to surface. I don't think we have them yet, but we will have languages at some point, I hope. At least some of my work is trying to move in that direction. That will enable good programming practices. And the other part is at the highest possible level, we want programs to remain readable for humans. And I think that compilers, how much information we provide users through the compiler maximizes their ability to solve problems. So quickly, I don't want to take also too much time, is that historically, having the right abstract machine solves about 80% of the algorithms development problems. I will talk about this a bit more in the following slide. All current quantum abstract machines are very good with simulators. That is a problem. And we need to figure out better ways of doing this. The second one is that there's a performance expressiveness trade-off that is universal and unavoidable. What we have learned is that how expressive power means how many problems you can solve with a given architecture. Performance is how quickly I can do that with how fewer resources. And we often have an ideal behavior of a machine. Expressive power is harder to measure. Of course, we have a limited set of quantum algorithms. My hypothesis is that that is the case because we have fewer qubits right now than that will be necessary. We're in this philosopher's disease space where we are mistaking a failure of imagination as an insight into necessity. And therefore, we probably need to remain open to how things should work. Performance seems to be easier to measure with benchmarks. We have predictive profiling, but we have actual bounds because of internal systems. So we need to become more realistic. And sometimes we optimize in one direction or the other one. But trying to get to the best possible realistic part historically has been a matter of having good programming practices. So one of the questions for me in quantum compilers is how do we enable features that lead to good programming practices that allows us to figure out better algorithms and better ways to optimize the ones we have. The other historical tendency is that, or lesson is that a lot of control, and I put control here in quotes for a very good reason. The boundary of control is shifting in quantum and FTQC especially. It tends to become control hardware in time. And this is something that if we extrapolate mentally from now to 5 years or 10 years, despite our ignorance of the subject, because we have to build the systems, many of those functions that we right now do in software because we need the flexibility to explore will become hardware. And this means we probably want to start keeping track in these compiler architectures of which features become really stable with time and mark them for possibly at some point greater translation into hardware. The other one is that we want opportunistic refinement, meaning that this is a very nice picture that we had a few years ago. We are learning that we have many more layers in this aspect. And I call that the hardware detail free zone at some point, because we have that necessity to integrate multiple modalities. But the point is that at each one of those levels, especially those enabled by the compiler, we should be able to make progress simultaneously. And therefore, one of the necessities is to have a very good definition of what interfaces look like across this time, across this stack. The other point I wanted to bring out quickly is that secrets are not high-level constructs. And this is something that we don't still have programming languages at the level that allows us to think in terms of instructions of the same semantic isomorphism to mathematics as it happens with classical languages. But it means we need to do the work. So my own criteria for this, and this isn't part of a paper that is coming or in writing, there's three requirements to match. One of them is that we need good annotational semantics that are isomorphic to the space of the problem we want to find. There must be representation independence, and this is where all the IRs will appear that may need to be annotated when we interact with intermediate level compilers, and we need to have compositionality. It is really hard at this point to know why quantum algorithms work. If you screen far away, all what you see is a series of blocks. That is not necessarily something that allows us to reason effectively. Another lesson is that when we start going at very large scales, I suspect that FTQC is going to push that to the limit once we cross many of the roadmaps by various companies. Is we are going to move into generation and validation, replacing something that looks like compilation today at very large hardware scales. So there should be some guidance, and it means that many of the components, one of the requirements that quantum compilers, new quantum compilers will pose, is greater autonomy from the infrastructure. So at some point, either the runtime will become more sophisticated, or some intermediate elements are going to become mediators between compiling and the runtime itself. That is not hard to foresee, I think. Another point is that we have learned to resist to optimize within differences that make no difference in compilation. So imagine that you have a quantum program, a bunch of circuits and a series of pulses, and you're tempted to only optimize at the pulse level. This happened in the very early stages in the system. What we have learned is that as we get larger and larger systems, this is ineffective, and we'd like to prune these programs to figure out simplifications and then continue to apply optimizations at the right scale with someone who is responsible for it. Another lesson and concern is that modularity and indirection tend to organize complexity. I think that the mid-circuit measurement optimization that Mike talked about are an example of this. But we also, I find it strange that we have not found too many quantum classical data structures yet. I would like to see, or I'd like to understand how the rise of those new data structures will manifest in the needs of the compiler. They have to appear. We just haven't found it because we don't have the right scales and we are very used to it. Now, converging to what I wanted to show you quickly, why do we want good abstractions? The first one is separation of concerns. I think we are starting to see that in the community. Not enough, but we are starting to see that. This is a diagram by Olivia Di Matteo, who is an excellent forwarder too. And I had the advantage to work with her in the project, collaborate with her in the project. We also want well-defined interactions between the layers, and we want that opportunistic refinement that sometimes we need to do that, and we need to do that responsibly. And then we'd like the beautiful edifice of classical quantum computing. Right now, sometimes it looks like this, right? Not exactly what we're looking for. So we've taken time to try to analyze how HPC has done it. There's a programming model where how computing has done it. There's an execution model, and there's a hardware model. And if you think about it, the programming model is telling Google Maps, take me from A to B. The execution model is, okay, give me all the turns and twists. And then the hardware model is press the brake and then the accelerator for 10 seconds and then turn the wheel 45 degrees. Of course, the bottom one is less productive. So we started looking into, there's something that's missing. And after many questions, what seems to be missing is that we don't have a good abstract machine. We reviewed all of those in classical computing. The orange part is the only one containing any description of the hardware. But if you look at all the abstractions in quantum computing, all of them talk about circuits. That is extremely problematic in the sense that we don't have a good idea of how to proceed. So we mapped all the quantum abstract machines, found that there's big gaps between 3 and 5, and one of them is that we don't have a very good type theory. We don't really understand how to go beyond shots. So we started moving in this direction. And the vision is the following, before showing the last demo. I think sometimes we have going through the intuition that we need to have a programming model that is as complex sometimes as the machine you're programming. That is completely the opposite in reality. If you take a modern microprocessor, the number of transistors is vastly not in proportion to the number of instructions, which is vastly not in proportion to the number of ways you can assemble a program. What this says is that most of the hardware is used to optimize very semantically simple instructions. I think that's one of the requirements at the long end, and that led to building a quantum abstract machine. We can talk about that more later if that's possible, or via email. But the idea was to propagate this. Was work funded by IBM in the IBM Discovery Accelerator Institute at the University of Illinois. And it ended up being a Rust product where Qiskit bindings are at the very bottom, but there's a concept of microarchitecture. There's a concept of quantum instructions that operate on registers. They don't operate on qubits. And I made it explicitly really hard to work with single qubits by having proper programming economics. So you take something that looks like x86 assembly. There's also instructions that are extended for quantum computing and hybrid instructions that allow you to perform ensemble measurements. And then the idea is to produce a very simple binary that executes on a virtual machine that then provides the inner compilation and runtime at the same time. So we've been able to demonstrate this on IBM hardware, run multiple algorithms, and then it also uses calibration data to internally at the microcode level to select the best possible execution layer or the best possible execution qubits that we can get. So finally, this looks like this, and I will end up. So right now you can build the program, move forward, and then it looks a bit like the 80s. I promise I will have something better but next time we meet. But you can look at the execution of the program, and then there's now processor flags that indicate when you are going into a quantum region of the program, then where superposition has occurred, or interference and entanglement have occurred in certain instructions, and then you can use that to expand the control flow instructions. Finally, this is my guiding vision. I think we have a lot to do, and we have multiple driving abstractions. Even at the level of original circuit to QECC, for me, that's still low-level abstraction, not high-level abstraction. There's a lot of work that needs to be done, because the more levels we have, the more we can trim and remove unnecessary work. As the last slide is by Fred Brooks. I think FTQC, the first systems we are going to build, we are going to throw them away anyways, but we are going to have to learn very quickly. And we are going to ideally not throw everything away. That's what he didn't say, but isn't done.